Hi guys, it's me again. Let us continue our discussion. Today I want us to talk about direct current, which is chapter 26. Direct current, it simply means a constant supply of current. You apply a constant current throughout a circuit, which is not the same as in alternative current, because in alternative current the current is capable of changing the polarity, so you can supply the negative and a positive current. So we'll only focus in direct current at this stage, and on the later stage we can now look at the alternative current. So direct current is sometimes referred to as DC in short. So you hear people talking about DC current, which is nothing but a direct current. So in any circuit you have what you call the resistor. In general, a circuit can compose of many components. You talk about resistor, you talk about capacitor, you talk about transistors, and so on and so forth. But then let us focus on the resistor. In a circuit, a resistor can be connected in two ways. You can connect a resistor being in series with one another, or in parallel with one another. So in series you have a number of resistors that are connected besides one another, next to each other. So this can be your resistor 1, resistor 2, and resistor 3. So in this circuit you apply a direct current, let's say I total. So because these resistors are connected in series, this current will be the same at resistor 1, resistor 2, and resistor 3. The current I total will be the same at I1, will be the same at resistor 2, will also be the same at resistor 3. So you can determine what is the total current that is flowing in this circuit. Also, you can determine the sum or the total of the resistance that is in this circuit, which I'll refer to as R equivalent. So R equivalent, or the R total, will be R1 plus R2 plus R3. And of course, if you know the current and you know the resistance, then you can calculate now the potential difference across all these resistors. So V total will be equals to the potential drop at each resistor. So it's I multiplied by resistor 1 plus the current multiplied by resistor 2 plus the current multiplied by resistor 3. And we just said that the current will be the same, therefore we can make the current common, multiplied by R1 plus R2 plus R3. So that's the first scenario. The second one, you can connect it in parallel. So you have resistors that are connected in parallel. This being your R1, R2, and R3. You provide a constant current, let's say I2, I total. So as you can see, it comes to a junction, and if it comes to a junction, it needs to split amongst the current that you have. So you have the current I1, you will have the current that is going through, that will be I2, and you also have the current that will flow in resistor 3, and that will be R3. So all these current, when they come to this junction, let's say at point B, this being your A, at point B, they need to combine, and they provide your I total will be the same as the initial or the current that was supplied. So what we're saying is I total in this case will be equals to the sum of all the current that are in the resistors separately. So I1, I2 plus I3, and the total at this junction, they need to be also equals to I total. And also you can calculate, as we did, your R equivalent, and your R equivalent will be equals to 1 over R1 plus 1 over R2 plus 1 over R3, etc., etc. So what about a potential difference? What about your V? So as you can see here, if you were to find the potential difference at point A and B, let's say you want to determine A and B, you will see that your VA B is equals to the voltage at resistor 1 will be equals to the voltage at resistor 2 will be equals to the voltage at resistor 3. So that's going to be V1 equals to V2, which is equals to V3. So you can determine the potential difference or the potential drop due to each resistor will be the same. So let us think about this for a second, just to digest what we've just said. Let's say you have a circuit, and in this circuit you connect a bulb, and let's say you have another bulb somewhere here, and another bulb, connected in parallel. And let's say I say this is your 3 amp, and let's say this one is your 2 amp, and I ask you to determine what is the current at A and what is the current at B. So let us apply what we just learned. You can start at any point. For now, I think it's easier to start here. You have the current of 3 that is flowing out of this bulb, which is 3A, and this current will go in this direction, and because what we said is the current will split equally when is connected in parallel. So you have current 2 that is going in this direction, and there's a current that we don't know which is coming in this direction, and the total here, they must be equals to the current that got into the system. So we have 3 that came here, 3 amperes, and that amperes will be divided according to the bulbs. Then here we need to find our 3 amp again. Therefore, this at current B, we simply find that is going to be 1 amp, because this is 2, so 2 plus 1, it will give you 3, and that 3 will go to this bulb here, and you will have resistor current of 3A, which is the same current that will be coming into this bulb. So I think it makes sense. If not, let us look at this one again. You have this bulb, and you also have this bulb, another bulb. Let's put another bulb here. Another bulb here. And for curiosity, let us put another bulb parallel to this one. And let's say this one is 1 ampere. Let me say this is 3 amperes, and I need you to find at A, and let me say this one is 2 amp. So I need you to find a current at A, a current at B, and a current at C. At C. And let me say that the current that I'm providing here is I total is equals to 8 amperes. Of course, if it's 8 amperes and it will be divided according to the bulb that I have, 1 here, 3 here, and here it must be 4 amperes, and that 4 amperes will be combined with 3 here, will also combine into 1. Therefore, the total current leaving this junction is going to be 8 amperes, and it comes to another junction, 2, it goes that side. Therefore, it means it's 8 minus 2, it needs to give you 6 amperes, and 2 comes this side, and this one also comes this side. Therefore, they will combine, or they will meet at this junction, and we will have 6 plus 2, which is 8. Therefore, there will be 8 amperes in this bulb. So I think now it should make sense. And all that we've just done right now is what we call the Kirchhoff's law. It's governed by the Kirchhoff's law. So the Kirchhoff's law is divided into 2. We have the current law and we have the voltage law. So we've just described now the current law, and the current law, it says if you have a node or a junction, the sum of all the current in the node, they must be equals to 0. As we just said, we have a node A at node A. So if I supply a current of 5 amps, and I have current I1 that is leaving the junction or the node, you have current I2 is also leaving the node, you have current I3 which is also leaving the road. So all these current, they must be equals to this current here. So let's say this one is I5. Therefore, I5 plus I1 plus I2 plus I3, they must be equals to 0, because the sum of all the current in the junction, they must be equals to 0. Also, if you have a closed loop with a number of resistors, R1, R2, R3, the sum of all the potential drops at R1, at R2, at R3 must be equals to 0. So if you have your VT must be equals to these potential drops here, which is I1 times R1 plus I2 at R2 multiplied by R2 plus a current at I3. So the sum of these, they need to be equals to 0 again. Now let's try to make some few examples and see if we follow. So let's say you have a closed circuit like this. This being your R1, R2, and R3. So let's say this is 8 ohms, this is 10 ohms, and this is 12 ohms. And I ask you to determine the total current that is flowing into the system. So there are rules that governs the operation of the Kirchhoff's law. What I always say is, number one, you need to identify all the nodes. Number two, you assign the direction of the current. Number three, you distribute the current according to the nodes. Then you apply the law. So number one, if you have a resistor like this and your current is moving in that direction, your current I, and your loop is also in the same direction as the current, so you will encounter what is said to be a voltage drop. In other words, you will have minus IR. So this simple tells you that the resistor that is here is going to eat up some current. So if you are providing 5 oranges, this one will take a certain amount of oranges and let other oranges passes. So similar thing that is happening. So the loop is in this direction and is in the same direction as the current, therefore you'll have a voltage drop. So if it's opposite, if you assign the group to be in this direction, then the current is in an opposite direction, therefore you'll have a voltage rise, and that will be positive IR. And also, if you have a battery, the negative and the positive, your loop is in this direction and the current is in this direction. So both the loop and the current are in the same direction and you are moving from the low potential to higher potential. It's more like you're charging up the battery, therefore you will have the voltage rise, which is positive V. But if you're going against the loop, so the loop, you have this battery, the loop is in this direction and negative, positive, and the current is in this direction. Therefore, it's like moving from a higher potential to lower potential. Take it as if we are discharging the battery. That will give you the voltage drop, and that will be negative. Therefore, if you know or you identify this, then it will be easier to solve the above problem. So now we have negative, we have a positive, and let's say this is a 12-volt battery and you are required to determine what is the total current. So you're moving from a negative to a positive, So you're charging up the battery, then the potential will be positive. Therefore, this is plus 12. Then let's say we identify, you can take any direction of the loop. You can take this direction or you can take this direction, but once you assign the direction of the loop, you stick to it. So this is my loop direction. It goes like this. So as you can see, the loop is in the same direction in the current at resistor 1. Therefore, I'll have a voltage drop. Therefore, it's going to be I multiplied by R1. Same as R2 is going to be I multiplied by R2 minus, the loop is still in this direction. Therefore, it's I equal times R3, and that should be equals to 0. Then you can substitute. This is my I is common, therefore this is I into R1 plus R2 plus R3 equals to 0. Therefore, this is going to be 12 to my I into R1 is 12 plus 10, 22 plus 8 is 30 equals to 0. Then you can solve for I, which is going to be 12 divided by 30 equals to 0. Then this is 120. Therefore, it's going to be 0.4 amperes. So that is the total current that is flowing into the system. That's how you find out the current if you have a network system like this. So we have one loop. You can make 2 or 3 loops, but I think that is beyond your scope. So right now, let us just stick to one loop. But one thing that you should master is these 4. Once you master these 4, you'll be able to solve any network theorem and using the Kirchhoff's law. Thank you.